the point, the data point n star which is closest to Q. Okay, so for example, you might have this Euclidean distance between two vectors x and y. And in this case, to compute this distance, it takes order d operations. And so this means that for, say, a collection of n vectors, finding the nearest neighbor is going to take roughly order dn operations. Okay, so we said before that this, it may seem fairly cheap, this thing, but it actually could be quite hard. It could be quite expensive. So if d is, 1 million, 10 million, or something like that, it could be even higher. Maybe there's music files or something like that. Who knows? Then that could be very expensive. So you might want to sort of limit the number of high-dimensional distance calculations you have to do. And you may also additionally want to say not necessarily have to scan through all of the data points to find the nearest neighbor. Okay, so this may seem a little bit weird. How could you avoid computing the distance between x and each, so between q and each of the x's, and still come out with knowing what the nearest neighbor is? So there are two things. You want to try to avoid the number of high-dimensional costly evaluations, and potentially we'd like also to avoid the number of actually scanning explicitly across the whole data set. So those are two not quite the same criteria. So if you can, obviously you have nearest neighbors, you can do all kinds of things with them. You can use it for k-nearest neighbor classification. Also, if you want to do something like k-means clustering, you also need to find the nearest neighbor there as well, as part of the algorithm. So this is a huge area, actually, trying to find your nearest neighbor quickly, and I have to confess I'm by no means an expert in this, so I'm a little bit unsure about some things here, but I think it's such an important topic that I wanted to talk about it here. Okay, so the first part of things we're going to discuss is some geometric perspectives, so based upon metric distances. Okay, so let's just define what a metric is. So if we've got, say let it the squared Euclidean distance between two vectors x and y, so we can rewrite this as, including this minus z and plus z. That's obviously true. You can then take the first term, square it, and the second term and square it, and we've got the 2 times by the cross term. So that's the transpose missing, obviously, on the one on the right. And then just using this notation, this sort of norm notation, that this is the square root of the squared Euclidean distance. Okay, so this is actual the real distance between 2 points, not the square root distance. Then we can just rewrite that similarly as the square of the norm here, plus square of this norm plus square of that, plus this scalar product between this difference between x and z and y. And given the fact that the scalar product can be written as the length of A times the length of B, so 2 vectors times the cosine of the angle between them, this gives us this expression here. Then we can use the fact that cosine theta is bounded between upper by 1. Okay, so this whole thing on the right would be less than that, and then you recognize that that thing there is just the square of x minus z plus z minus y squared. Okay, so then you can take the square root on both sides, and you're left with that the length between x minus y is less than the length x minus z plus z minus y. Okay, so this is this thing here is called the triangle inequality, and basically all it's saying is that if you want to go from x to y, it's fastest to surely go from x to y, or from x to z, and then z to y. So it's a kind of intuitive thing. Okay, so that's what the an inequality, a triangle inequality that the Euclidean distance satisfies. Okay, so more generally, a metric is defined to be some kind of distance, some non-negative number, which has got this property that the distance between x and y is less than the distance between x and z and y and z. So the Euclidean distance satisfies this, but there are other distances as well. And additionally, we need it to be symmetric in its arguments, So dxy is the same as dyx, and we want it to be non-negative as well. So just to bear this in mind, so it's the Euclidean distance, so the length between x minus y, which is a metric, and not the square of that. So the squared Euclidean distance is not a metric. Okay, it's just you do need this square root there. Another thing to be aware of is that people use this term metric a lot. So mathematicians, they have a precise meaning for the word metric, which is this. And then you particularly has to satisfy the triangle inequality. And many other people in science and engineering don't use it in that way. They just, when they say metric, they simply mean some distance measure. So there's a kind of common abuse of terminology there. But here we really mean this mathematical definition of a metric. Okay, so we're going to look at this metric distances now, and we're going to try to figure out, first of all, if there is a way to avoid, for a query, Q, calculating all of the distances to each of the x's in the data set. Okay. And we're going to use some bounds, basically, to try to do that. So, first thing we're going to do is define some bounds. Okay, so the first thing I claim is you've got x and y, and you've got also the distance between z and y. If the distance between x and y is less than half the distance between z and y, then you know that the distance between x and y is less than the distance between x and z. Okay, to prove that, for a metric, we have this inequality. So the way to sort of visualize these things is that we've got yz here, and we just insert x. Two things. So this x here, if you remove it, gives us the distance between, say, y and z, and then we're just adding these two to get this bound. Okay, so this is one thing we can say. So if you're in the situation that this distance here between x and y is less than half the distance between z and y, then you can similarly say, well, the distance between z and y is bigger than or equal to 2 times the distance between x and y. Okay, so we can plug that onto here. So we're bigger than 2 times by x and y here. So 2 times the distance between x and y is less than this bound here. So we just subtract this from this. So we've got the distance between x and y is less than the distance between x and z. Okay, so this is an interesting thing to observe, because it means that if you're in that situation, you automatically know that the distance between x and y is less than the distance between x and z. So in other words, you don't have to compute this thing explicitly. So if you said, if I'm in that situation there, I want to know if x is closer to z or not. Well, the point is I don't need to calculate the distance between x and z, because I can infer it from this property. It's a metric space property that you can exploit in that way. So here's an attempt to visualize this. Let's look at this for some sort of nearest neighbor setup. So the point here is that you've got, in this situation, you've got a query Q, and you've got a point xi in space. Okay, so one of your data points. And you may have, say, some distances between these points xi and xj. Okay, so we're going to assume, first of all, let's imagine somebody gives you, as pre-computed, say, all the pairwise distances between the points in your training data. Okay, so you have access to that. And then somebody says, well, let's imagine that the distance between Q and xi is less than half this distance there. Okay, then actually I know that the distance between Q and xi is less than the distance between Q and xj. So I don't have to go and compute the distance between Q and xj. I know that basically it's further away from Q than I is already. So the way to sort of potentially visualize this is to say, well, here's xi, and the distance between these two xi's is this. Okay, so basically this is the distance here between Q and xi. So if this is half the distance between xi and xj, so basically if this Q point here were kind of here, right, which is bigger than half the distance between xi and xj, it could be that this q is closer to xj than it is to xi. That's possible, right? But if it's less than half, then even if you were to sort of say, well, actually, you know, xi could be, whatever it is, there's no way that if you were to add on q over to here, that can be closer to xi than as xj than it is to xi. Yes, I find it's very hard to visualize actually. Anyway, you can think about that. It's mathematically true. Anyway, that's the good thing about the mathematics, that we don't have to worry too much about the picture. Anyway, feel free to think about that in your own time. But this is true. So the cool thing, the point is that if you've evaluated this distance here, right, and somebody tells you this distance here, if this distance here is less than half of this distance, you don't need to compute that distance. You can avoid it. I know automatically that this is closer to that than it is to that. So the key point then is how to use this result in a more, you know, to bootstrap that, to avoid doing some of the calculations. Okay, so this is a busy slide, but this is a classic algorithm called Orchard's algorithm. There are many similar kinds of algorithms around, and I'm not sure if it's really correct to attribute it to Orchard, but maybe it seems to generally be done, but certainly people have been thinking about similar things for quite some time. So the idea is that first of all, we do something very expensive, which is we pre-compute all of the pairwise distances. So we form this matrix Dij, which is the distance between all the training points. Okay. So this is a one-time calculation that we do once and for all, and we store this matrix Dij. Okay, so that's expensive, but it's just a one-time thing. And then what we do is for each data point, xi, we form an ordered list of which are the points in the training set which are closest to xi. So this means that, this is a bit tricky notation, but the li is the list for the ith training point. And the first index in the list is the other training point which is closest to xi. Okay, and then the second one on the list is the next closest training point to training point I, etc. Okay, so we rank them, we order them by closeness to xi. So each data point will have a corresponding list of which are its closest data points. Okay, so we form, again, this is a kind of a one-off pre-computation that we do, and we store these lists and the corresponding distances. Okay, so now we've done that pre-computation, we come along with a query Q, and we want to find the closest point in the training set to Q. So you just start with some guess for which could be the closest point. So you guess, say, xi is the closest point, right? So then what you do is you go to the list li. Okay, so what this says is that if the distance between, for this, you calculate now the distance between q and xi, you actually compute this thing. Okay. Now, from before, we know that if the distance between q and xi is less than half the distance between xi and the first one in the list, okay, then this one in the list cannot be closer to xi than to q than xi is. It's not possible. Okay, and if that's not possible, because this list is ordered, then none of the other elements of this list can be closer either. Right? So what that means is that you automatically you found the nearest neighbor. Right. So that's a really lucky situation that you just found this thing, you check this bound. If this is true, then you're done. You're automatically finished. Okay, so that's a very lucky situation. But you can see that we then inferred we made only one distance calculation, and we automatically know it's the nearest neighbor. So that's the extreme fortunate case. So in general, what's going to happen is that that first element in the list is not linear, is not going to satisfy this relationship. Okay. So what do you do then? You move on to the next member of the list. Okay. For list I, and you So yeah, no, we don't move yet. I don't think this description is quite correct, actually. Yeah, I think it's slightly worded a little bit weird. What we have to do is that for this member, because this is not the case, right? It could be that this first member of this list is actually closer to Q than xi. That's possible, right? We cannot rule it out. So we need to compute that distance now. Let's say, now we compute that distance and we compare that distance to our current best distance. And because I've calculated this one, right? So now I calculate the distance between Q and the first one in the list. So then I will know actually whether or not the first one in the list is actually a better distance than my current best distance. Okay. If it is, then what I'm going to do is I'm going to jump to a new list. Right? So let's say let's make this more concrete. Let's say I'm going to call this list the first member x1. Okay. So what I've done is I've then got this xi is my current, my initial guess as to which could be the closest one. So it computes this quantity, right? This is q and xi. If this is true, I'm done. If it's not true, I compute the distance between q and x1. The distance between q and the first member of the list. Right. And if that distance is lower dq and x1 than dq and xi, it means that the x1 point is closer to the query than xi is. So this is a better data point, it's a closer data point. So what I'll do then is, okay, that means x1 is better. So what I'll do now is I'll jump to the list for x1, which is L1. Okay, now repeat this process then, starting from L1. So, okay, so that's a list jump. If x1 is not closer to q than xi is, I move to the next one in the Li list. I need to move to the second point of the list. Okay, and I carry on checking again. If the bound is satisfied with this, I'm done. Okay. Otherwise, I check if it's a better data point. If it's a better data point, I jump to the corresponding list for that data point. Okay. If for any list I get to the end of the list, then I'm done as well. Once I've traversed to the end of the list, I've traversed through all affected data points. That means that I've found the nearest neighbor. Okay, so the way this works is you've got this collection of lists for each data point, for all the data points. You start somewhere on a list. You keep walking along the list until you either done, you found the best thing because of this inequality, or you found a better candidate than your current one, and you jump to the start of the list for that candidate. And you keep walking around these and traversing these lists. Okay? And this is called Orchard's algorithm. Now there are many, similar algorithms basically. Yeah, so it's a bit. It's not such a complicated algorithm, but it's a bit difficult to explain. So there's some rough. I find actually I have not completely understood all of the ramifications for the complexities of these algorithms yet, but just very vaguely, of course, we can see that this thing here requires a pre-computation for the Euclidean distance, which is going to be order dn squared. Okay, because you've got to compute all these pairwise distances, and each distance takes order d. Now, as you're doing the list walking, then you've got to evaluate potentially as you go along with each point in the potentially want to compute the distance between Q and a member of the list. Okay, so that's going to cause you order D operations to do that, because you've got to calculate Euclidean distance. So that means that you keep walking along, and it's hard to say exactly what the complexity could be. If you're super lucky, you just have to do one distance calculation. You already jump into the correct sort of list. If you're really unlucky, actually, you have to calculate. If it doesn't help you at all, you have to go right to the end of all the list. You have to do n data points. Okay, so it's hard to say exactly how many evaluations you'll need to do. It depends upon the geometry of your particular data set. But at the worst case, it's kind of not much worse than explicitly doing the list, and maybe a little bit worse, but explicitly evaluating all of the distances. And if you're lucky, it'll be a lot less than that. So we'll see some, maybe not today, but when I run the experiments, you'll see that for the low-dimensional dense data, this algorithm is very efficient. That you can typically get away with, instead of maybe an order of magnitude less distance computations than you would otherwise require. So this algorithm can work very, very, very well in that case. So what's cool about this is that you don't have to, you're hoping that you don't have to walk through the whole data set when you come in with a new query. Okay, so that's the advantage. And the disadvantage is this large storage cost here. Yeah, I said that. Okay, so that's one thing you can do. Here's another thing you can do. These things are getting they're going to increase in complexity. Probably my ability to explain them will decrease correspondingly. But we're going to look at another bound, okay? So we want to, basically the point is we want bounds, like, for example, that you can say, well, based upon these things, I can tell you that the distance between some x and the query is bigger than some number. It's got to be bigger than that number. And if I've already calculated, say, some current candidate best distance, let's say it's 3, and I can show that the distance between x and the candidate, the query, and some other x is bigger than 3, then of course I don't need to calculate that distance explicitly, right? So lower bounds are useful on these distances. Okay, so the question is, what lower bounds can we get out from these metrics? Well, we know the distance between q and xi is less than the distance between q and xj plus the distance between xj and xi. So just flip that around to say the distance between q and xj is bigger than this distance here. Okay, so this thing could be negative, but it doesn't matter too much about that. You could, if you want, to put a minimum of this distance at 0, but it's not really necessary. Okay, so what we're going to do now is we're going to say, well, let's imagine that there's a subset of the data points for which you've already calculated the distance explicitly between the query and each of those xi's. Okay, so I'm going to call that, say, a set of indices I for which d, q, and xi has already been computed. Okay. And then what I could do is I could say, well, look, that means that for each of these i's here, I'll get a different lower bound, and ideally I want the biggest lower bound that I can get, right? This is the best, if the distance between q and xi is, if I've got candidates, 1, 2, and 3 distances, I want to say, well, the distance is bigger than 3. That's better than saying the distance is bigger than 1, right? I want to sort of bound as far away as possible how far xj can be from q. So I want to find the best bound amongst the set of possible bounds. So I can maximize this bound over the collection of distances that I've already calculated. Okay, so remember that this d xi and xj is something that I'm also going to, for similar to Orchard's algorithm, I'm going to assume that you maybe pre-computed that distance matrix. Okay, so this is like just dij, and then you just need to calculate this distance between q and xi, and we're assuming that we've already calculated that, so that's already done. We've stored that as a spreadsheet. Okay, so if you've got this now, and let's say that you've got a current best distance. So you've got some candidate, and you know the distance between that candidate and the query. Let's say it's 3, right? So that means if there's some xj whose distance is say 4 to the query, you can show it's bigger than or equal to 4 by this bound, then clearly it's worse than 3. So you can discard it. You can eliminate that data point from consideration. Right, so this is the elimination part of this algorithm. So we use it like that, and in principle now, we know I could do this for every data point to get a bound on the distance between the query and every data point. Okay, and then I can use that from knowing what my current best distance is. I can then eliminate hopefully a large number of data points because their lower bounds are greater than my current best minimal distance. Okay, so that's essentially the ESA algorithm. And then when I go on to another data point, well, okay, maybe I'll explain. Yeah, okay, so, all right, so let's say that you've done the elimination step, right? So you've got rid of all data points that cannot possibly be closer to your query than your current best candidates. You look at the remaining set of data points, and basically you now have to make a guess as to which of those remaining data points you want to examine next. Okay, and the way to one suggestion, which is the ESA algorithm, is to pick the data point which has the lowest lower bound. Okay, so this is like the lower bound in some sense is like a surrogate. It's like an approximation, if you like, of your actual real distance. So you go to the lowest one, the one which appears to be smallest according to your approximation. You start with that one. Okay, so in other words, you rank your data points according to this list. And you start to the nearest, what would you believe to be the next nearest according to this lower bound distance. Okay. So there are many kind of questions here about whether or not you really need, whether or not you should include a large set of data points here, or as you incrementally increase the number of distances you calculate, do I really need to update this, or should I just keep a fixed number? Or, I'm not really familiar enough with this literature to tell you what the word on the street is about the best thing there, but you can imagine there's all kinds of different schemes you could consider. One thing that's kind of bad about this, I think, is that when we do this situation here to do the elimination, we're actually going to run over all of the data points in the list. We're not calculating the distances between the query and all the data points in the list and the data set, right? I don't do n high dimensional calculations. So let's say, to make it more clear, let's imagine you start off and you haven't calculated anything yet, no distances, okay? Except you come along with I as your first candidate nearest neighbor. So you calculate this distance d, q, and xi. These ones were already pre-calculated from your matrix. Okay. Then what this would require you to do is to run over all j, which is not equal to I, or in other words, all the n minus 1 other points, and you calculate this lower bound. But there's no high dimensional distance calculation required to calculate that bound. But you are running over n points, over n elements. You see what I mean? So it's not a high dimensional calculation, but there are a large number of fast calculations to do here. So that's not something that you would have in the orchard algorithm. You see what I mean? So these are kind of distinct aspects of complexity here. Okay, so that's the approximating, getting an approximate distance or bounding distance, and the elimination algorithm. Do you keep going on like that?
Excuse me.
Yeah.
One question regarding the slide. So the right-hand side says we go we look for the maximum, and
Yeah.
the first distance is the distance between Q and all the other points.
This one here.
Yeah. So it means that we would have to go over all, because if we do that, then
Yeah.
we have our answer, right?
Yeah, so, okay, this index I is not all of the data points. It's all of the data points that we've currently computed the distance for. So let's start right at the beginning.
Okay.
So let's say that you guess that xi, that's your first guess. Okay, so you compute dq of xi. That one you have to do. At that stage, this set I here is just containing little I. It's the only one you've currently computed. Okay, so in that sense, this max is this set is empty, or it's just got the one member. So what that would mean then is we would just have that for the initial stage, and then we'd have to run over all j. So for all of the other data points, which are not equal to I, we compute this right-hand side. But I've already computed that, that's fixed, right? Because I is not changing now, we're iterating over j. I'm just computing, this is actually the only thing that would update. So then I'd run, this is a very fast calculation, this is just a couple of, it's just two summations of real numbers. So it's lightning fast, this thing. You have to do it n times though, which is a little bit bad, but probably this thing is easily, it's super fast usually, but it is formally an order n calculation. It's an order n, order 1 operations to do this summation and differencing. Okay. So I'm not computing all of the distances between q and each other. It's just running this formula. And then what I do, though, is I will, I'll use those distances. I mean, I will hope that I will be able to eliminate some data points based upon these distances. If I cannot, though, well, I've eliminated some, and then I'm left with some other subset of the training points. And now what I'll do is I'll need to figure out, which is my next best candidate I want to examine. And I'll use these lower bounds as kind of surrogate distances between Q and all of those points as my guess as to what to examine next. And I'll choose the bound which has got the lowest value, because that's kind of my guess as to what might be the closest neighbor. And then I'll repeat this thing. But so that might be, say, xi primed. Now I have to compute the distance between Q and xi primed. So now I'll have two distances that are computed. So this subset I, the set I, will now contain I and I primed. I can run over this maximization now. So this number of maxes here is in potential of growing as I've calculated each distance in the past. So there are questions there about whether or not you really want to grow that, because that will increase the complexity of computing these bounds at each point. But then there's a trade-off, because the more you include, the more you may be able to eliminate, because the bound is getting tighter. So I don't know, quite what the best strategy would be there, but it's probably very deep. It could well be heavily data dependent as well. But yeah, it's not easy to, I think, formally understand what the best thing would be to do. Yeah. But that's essentially the ESA approximating and eliminating algorithm. Okay. I'm doing for time. Oh, we're almost done. So let me just show you, before I go on to more complicated things, let me show you a picture. No, that's not good. So there are some things in this picture which I've not explained yet. But this is obviously two-dimensional data, so this is kind of an easy case. And the blue dots are the data points, and the green cross is the query points. It's here. Yeah, this is not maybe so. It's maybe not the greatest plot to show at this stage, actually. But the point is that maybe I'll explain more about this next time. But there was, as you can understand, there are ways of eliminating data points here, and I'll talk about other ways of eliminating data points. And the ways that this is working is that I managed to eliminate where there's a cross. I can sort of geometrically understand that I have not computed the distance between this query point and any of these crossed out points. I just know that they cannot be closer than these blue dots over here. So I managed to eliminate a large amount of the space. Okay. So what, maybe we'll leave it there for this time. What I will talk about next time is more complex, slightly more complex extensions of these two things, which have got kind of increasingly complicated justifications about whether or not they're really useful or not. I'm not completely sure about it. And then we'll discuss another thing which is called a KD tree, which you may have you done KD trees? You did that, KD trees with Mark? Or, no. So we'll talk about a kind of what's called a hierarchical data structure in computer science, and called the KD tree, which is another method for approximating these distances.